It's a pleasure to introduce Professor Stephen Smale from the City University of Hong Kong. We've heard this morning in Smale's own words about his not completely successful attempt to prove the Poincare conjecture back in the 1950s. But of course, he had a stunningly successful proof of the generalized Poincare conjecture in higher dimensions shortly afterwards, this was intimately connected with his proof of the H-cobordism theorem, which is one of the most fundamental and important results in high-dimensional manifold theory. But beyond these vast achievements in topology, Smale has very broad interests and contributed to an enormous range, from economics to theory of algorithms to complex function theory and much else besides. He's also produced famous lists of problems, and perhaps that will be something what he's about to tell us about today in his talk on problems in topology post-Perelman.
Well, thank you. It's a testing. Is my microphone working okay? It's a great pleasure to be speaking at this celebration of Perelman's great result on Poincare's conjecture. I'm also happy to be speaking in this room as an old sea captain. It's a great pleasure to be in front of such a great sea picture. So I want to take another look at these questions that have been talked about today, a little different. We should try to remember that Poincare's conjecture came out of a series of papers of Poincare, analysis, situs, and its complements. And that was a great part of what Poincare had done, but simultaneously and inseparably from that was Poincare's development of topology itself. In particular, he did fundamental group and mathematical foundations of topology. And that came from some various inspirations, partly group theoretic questions in mathematics of his own, and otherwise from developments in differential equations, looking at the topology of dissipative differential equations, which had become more and more into the forefront of those years towards the end of the 19th century. So my look at these questions in Poincare's papers, especially homology theory, I want to take a new look at that in terms of this age of computation. There is, I think, a revolution in science in the last decades given by computation. I think computation itself has given a great unity to science because it's brought together so many similar lines and disparate branches of science. And I think mathematics has a role to play in the mathematics of computation. So that's my main interest, is the mathematics of computation. Not applied mathematics, but the mathematics of understanding computation as a physicist would, not as an engineer. Okay, so what does that have to do with homology theory? Well, I want to give what Shmuel Weinberger talks about sometimes, quantitative topology. As an illustration towards that, there is I think in some ways, the probabilists, the statisticians, have gone way ahead of mathematics in the sense of quantifying, making more algorithmic some of the main ideas in topology. And let me illustrate by just taking 1 over m, the sum of x over x belonging to a finite set. This approaches the integral of f, say d mu. Under these conditions, f is a function on a probability space, x, real valued, with the probability measure mu. And the central limit theorem says if x bar is drawn at random, we can expect this as x bar gets larger and larger draws, you can expect this to work in probability. So that's classical statistics revolves around this asymptotic picture. But also, some time ago even, there was quantitative versions of that which have developed vastly in the recent decades through concentration inequalities. And the idea is we take, instead of looking at this, the asymptotic behavior, the limit, which is certainly not very computationally oriented, we take this difference for a given m. We want that to be less than epsilon with probability 1 minus delta. So delta will depend on epsilon and will depend on m. So Chebyshev already has given some quantitative estimates of what how to write down delta, so this is true. As a function of epsilon and the variance of f and the size of the sample m. M is the sample size. Okay, so that's pretty old Chebyshev. I certainly don't come from statistics or probability, but this paradigm, I think, has played a wonderful role in eventually what we call learning theory, which is now something that's useful in almost all the sciences. It's a kind of a modern version of sampling theory or statistics, which mixes in mathematical properties of f in this estimate. So for example, already Bernstein got exponential speedups of this if one put a bound on f. If one put a bound on f, L infinity norm, say, then one would get a much stronger version than the classic Chebyshev. And if one puts more and more properties on f, so one thinks of putting some topology on x, more properties on f, some kinds of norms, then one leads to some of the big developments in learning theory, which has got eminent applications across science. Okay, so that's a model for what I would like to see in homology, even as formulated back with Poincare. So I want to redo homology in the same kind of spirit in this quantitative way. So let me give heuristic examples. Suppose we take a circle, the plane if you want, but this is not really the circle as you're thinking of it. I want this to be a circle of a finite set of points which are epsilon dense. So epsilon, say, is like a 1,000th or maybe 10,000th. It would look the same. Okay, so imagine this is, well, I can write out a easier to visualize picture, finite set of points. Okay, so now traditional homology theory says that the homology theory of this or this, any finite set of points is trivial in dimension greater than 0. And so somehow we've lost the circle. We lost the cycle. Here we have h1 of x equals 0, and this is traditional homology. I want to say h1 of x equals, say I work over the real numbers, equals r, coefficients, real numbers. I'd like to say this, because that will catch the geometry of this pattern of data. Okay, so that's the goal of this construction. So I want to talk about homology which says this result. It's going to be a different kind of homology theory and how to do that. And I should say this was developed with Nat Smale over the last couple of years. Okay, so what I think is important, what we do is put in a scale. So we have a scale, lambda, let's say alpha. It's a scale positive. It's related to multiscale, like wavelets and persistence homology of Carlson, but it's not. It's homology at a single scale alpha. And what we want to do is use homology at a single scale to catch this fact. We have a one-dimensional class here. Okay, so now this is heuristic because I haven't defined such a group. But now the scale has the following heuristic picture. If we stand back far enough, maybe at the end there, well, not even there, this will just look like a blob, a connected. You don't see the hole here if one stands back far enough. At least if this is a little thicker, a little thinner, a little smaller radius, you don't see the hole from a distance. So for alpha large, this would still be trivial. For large scale, this would be trivial. Okay, now if we get very, very close here, and even here, if we look very close to that picture, we see all these little atomic particles, all these dust here. So we see this is just essentially a finite set of points. So for small alpha, this will be 0 also. But for alpha in the intermediate range, roughly less than the diameter of this set, and bigger than the distance in some sense between these points, then we will catch this cycle in the homology. This is inspired very much by the role of data. So a lot of what we're doing is trying to understand data. Data is an integral part of scientific computation. It plays a role everywhere. Understanding data has become such a big problem. So what does it mean to have a pattern in data? And what we're doing is trying to give some mathematical foundations for saying what is a pattern in such a set of points. Here we see the pattern this way expressed this way at a certain stage alpha. But before we, at a finite set, we need to specify the scale before we can say anything about homology or the pattern. So that's the motivation. Okay, so now what I want to do is to formally define the alpha homology groups. And we want to do this very generally. We have a space X, and let's make it simple in some ways, compact, metric. Space. We're given this, and soon enough I'll be using a probability measure, but maybe not immediately. But it's always in the background. So I'm given this, and I'm given a scale alpha. So this is a probability measure, mu. Okay, from this I wanted to construct these objects H sub alpha, graded, so H1, H2, H0, and so on. I want to define those. That's the goal. So this is going to be given as follows, of x at scale alpha, which captures what I've spoken of here. Okay, so what we do is we take a cover. We take this cover, B alpha of x, x belonging to x. Okay, this is a covering. Take a covering of open sets. And now we can take the nerve of this cover. So this has got a associated simplicial complex. This what's called the nerve. So we have a simplicial complex. A lot of people will be a little uncomfortable because this is not a finite cover. It's highly infinite. So this would be a simplicial complex with a continuous number of vertices. The vertices will be the points x. So that these will be the points, the vertices of our simplicial complex. Nevertheless, this is discussed in Eilenberg-Steenrod. So there is a perfectly good simplicial homology theory associated to this as a simplicial complex or the nerve of this cover. So for finite covers, this is everything every topologist learns very quickly. For infinite covers, some topologists, and even in the very old days, I don't know if they actually worried about this. Both. Either one. They're different. They're different. Yeah, we do both. Okay. But for the moment, let's just take the homology, okay? Eventually, we work a lot with the cohomology. But we'll take the homology for the moment. Okay, so this defines such a space, and we have this works for all orders. So we can put an L here. L equals 0, 1, and so on. So these define, this is our definition. I put nerve here. The nerve of this cover, the homology of X is the homology of the nerve of this cover. Okay, so this is the construct that I suggest is of interest. Okay, and I want to now make some argumentation towards that end. For one thing, you can check it behaves as like suggested for this example. Okay. So here's a question. Dimension h alpha of x finite. I don't think too many of you will have an answer for that. It took us a long time, well, to formulate this question and a much longer time to get some answers. Well, immediately we could say a especially important case is where X is finite itself, a space of data, a set of data. So if X is finite, then this construction is just a finite covering, and certainly, yes. Okay. Then what Nat and I proved was true dimension 0, 1. Not, well, order L equals 0 or 1. Then it's true, finite dimensional homology. And then there was a topology conference of topologists especially oriented to this subject, organized by Shmuel Weinberger at Chicago. So I gave a lecture of things at this point, and I asked this question, is this always finite? At that time, we didn't know the answers, so we said, maybe it's always finite for any space X, any alpha positive. And the idea is that the local structure with alpha positive is kind of blurred over. So you don't see local pathology coming into the picture very easily with alpha positive. Okay, well, subsequently, I gave a talk in Rutgers, this topology data type thing. I asked this question, and a month or so later, I got an email from Baker, Anthony Baker. The answer is no for L equals 2. Two-dimensional homology can be infinite. So it's not very hard, it's hard enough. It's a hard enough example. So I don't think I'll try to explain it here. It's an infinite number of points. It's a countably infinite number of points. It's 4 sequences with a single limit point. So there's only 4 accumulation points. And it's a pretty example. I don't think you could write something like this. You write such a two-dimensional simplex, and then you use the fact that the boundary of this, well, I don't think I can go into it, but it's in our paper. There's a reference to this in our paper. This is a 4-person paper, which I'll go into in a minute. It's on my website, CityU, and the authors are, besides Nat and me, it's Schick, Bertoldi, and Göttingen, both of them at Göttingen. So let me, so there we have as an appendix Baker's example in dimension 2, where you have infinite dimensional homology. And still, the question remains, after a long time, to try to find conditions under which this is true. For example, on a Riemannian manifold, is this true for a dense set of alpha, or almost all alpha? It seems that we worked on that, Nat and I worked on that a lot without success. Smooth Riemannian manifold, is this problem solved positively, generically? Because I think Baker's example could be modified to be on a manifold. Okay, so you can ask questions if you like. So this is a question I especially want to pose in this audience under some kind of general conditions or any conditions or results on this problem. Because I would say this is more or less wide open, except there's enough examples and results to show that it's not trivial. Okay, so I hope this you understand this picture okay. Now I want to give a motivation. Well, I'd say maybe the basic motivation is because of X's data. Data comes in thousands of ways, from the universe, from medical imaging, and one would like to see some patterns in that data. Patterns which have some kind of geometric importance because they could help give some kind of a clue to the physics of the universe that generates some of the data, or many things. And this data is always going to be in such high-dimensional space that we can't see these simple pictures of that circle of points. You can't see that in the data because it's in hundreds of dimensional space. But if you have good algorithms for computing this for the finite set, then one would have some way of understanding the geometry of data. I shouldn't say geometry of data. I should say the topology of data. Because there's another question, the geometry of data, which I want to get to. OK, and now there's a broader picture. We see, as most people, I think, in learning theory, see data is something that is drawn from an underlying probability distribution. This is very similar to the way that mathematicians think about things. There's a Platonic universe, which we don't see. But in this case, it is this probability distribution, generally continuous. And what the data is, what the empirical side of that underlying reality. So one wants to see that underlying reality. And one can see that through the studies of these groups, and moreover, how these groups behave as x changes. For example, if x is a finite draw of data, and one would like to take a new draw, maybe more data points, and understand how the homology group changes. So those are the kind of things that go into this. And more precisely, that comes out in the following. So the way we started this project, Nat and myself, was there were a lot of considerations coming from vision, Mumford's work, Gunnar Carlson's work, and vision, where they found in certain small images in the real world, probability distributions were sort of carrying some kind of surfaces or some kinds of cycles, some kinds of geometric patterns. So that was a question of working with the finite data and a lot of work. They found these homology groups. Not exactly the way I'm talking, but in their own way. So, and another leading result up to this was work I did with Shmuel Weinberger at Chicago, Partha Niyogi at Chicago, and that was where we take a manifold contained in Euclidean n-space. And we want to recover the manifold. And we suppose the manifold is represented by some kind of oracle, which allows us to draw at random points from the uniform measure on the submanifold. And so we eventually proved results that you could, from a random draw of points here, depending on curvature, type, and variance of the manifold, one could get a complexity theory with high probability to recover the homology of the manifold. Okay, so that's background for what I'm saying. But then there was, with all these things, there were some big problems. First of all, one cannot expect data or probability distributions to lie on submanifolds. That's a very strong hypothesis. So we want to get away from that very strong hypothesis of data lying on a manifold. It could lie in the singular space. Not just the data, but the underlying distribution lying on a manifold is a very strong hypothesis. So we want to get away from that. A second consideration is topology is only a first approximation And what I mean by that is the results of Hodge in the 30s. Hodge tells us on a manifold setting, smooth manifold, Riemannian manifold, that in every homology class on the manifold, there's a unique, or say cohomology. One goes back and forth between cohomology and homology and things I'm saying now. In each cohomology class, there's a unique harmonic representative, a solution of a partial differential equation. Rigid is given by an optimization. So it's got a very tight geometry. So Hodge theory gives a transition between this very flabby topology and the very rigid geometry. So Hodge theory could give a lot better answers to these questions of Weinberger and Niyogi and myself, as well as to the results of Mumford and Carlson. So because of that, what we did, Nat and I, again, this is a reference to this paper on our website. We developed some kind of Hodge theory. Which covers these situations. So we have a Hodge theory, which is a first approximation. It's as general as this. We take a compact metric space together with a probability distribution and alpha. And we define a Hodge operator of order L. And it goes from L2 of, let me just write L2 for the moment, to L2. This is really going to be, I'll be a little precise here. It goes from this space to U alpha L, where U alpha L is the neighborhood of the diagonal and x to the L. So we define a Hodge operator in this generality. Now I'm covering over a couple of points here. And so with this Hodge operator, the solutions of this can satisfy, give answers to questions I have raised. If we take a finite set X data set, then that will give us results on the corresponding homology and geometric representatives by solving this applied to f equals 0. So we essentially solve this equation. This isn't too bad to solve in principle because it's a linear equation. Okay. So I want to come back now to be a little more careful about what this is. It's easy enough. We take U, this is just a neighborhood of the diagonal. Yeah, contained in XL. Set of all points with an alpha of the diagonal. And the induced metric here. And I want to define a co-boundary map. HL, that goes L2 U alpha L to L2 U alpha L plus 1 for all L. Okay, this is defined just in classical ways from topology. It generalizes the so-called Alexander-Spanular co-boundary map. Or it could be reconsidered as a check map. And what we do it on L2. Usually it's done on just abstract sets. But here we use it on L2. Okay. So on L2, well, we can check that this coboundary squared equals 0. So it defines already a cohomology. Cohomology groups are defined. So these are going to be the cohomology groups that I'm talking about here rather than homology groups. And now, what we did, we assumed the image coboundary is a bounded operator on Hilbert spaces. And so, at first we didn't know we had to assume it, but we eventually assumed the image of coboundary is a closed subspace. So assuming that, the image of coboundary is a closed subspace, then one derives a Hodge theory. One gets a pretty complete Hodge decomposition. This is defined, and so you have a full-fledged Hodge theory in this situation, in this setting, provided this condition is met. Now, one could replace, well, I should say now, this is not always met. And it's not easy to see why. It took us a year talking to many, many analysts to understand that. Eventually, we had a mistaken proof that this was always true. However, Schick, a person from Göttingen, found a counterexample, a very subtle counterexample, that this is not always closed. So then we joined forces with Schick and his colleague Bertolli at Göttingen, and they got us started on using a spectral sequence type arguments by complex arguments to analyze situations where we could prove this, and even more, this cohomology, L2 cohomology of X is finite. This implies this. So that paper, in that paper, we prove, for example, for small alpha on a Riemannian manifold, this is always true. And so we have a Hodge theory for small alpha on any Riemannian manifold. And that, in a way that we know, partly Nat and I have studied that a lot, and we have some ideas of how the correspondence works, but still a lot of things we don't understand. The relationship of our Hodge theory is alpha goes to 0 and Hodge's theory itself. One goal is to try to prove the classical Hodge theory from ours as some sort of limiting process as alpha goes to 0. That's not done. Okay, so the upshot of what I'm saying now, if we assume this condition, finite dimensional cohomology here, if we assume that, then we get the Hodge theory, and then we get the solutions for these problems that I was suggesting before. We can deal with finite data sets and their infinite analogs on a compact manifold for So all this works for finite data. Of course, this is true. And this recasts a little bit of a Hodge theory of the 30s, Benno Ekman. He had a combinatorial Hodge theory after Hodge. But it was a much different way of looking at things. Both in common, though, have a simplicial complex underlying the Hodge theory. Okay, and also there's so many things I'm not saying about the history. There is the work on a graph. In the graph, one takes the vertices to be the points x, finite set, and then the graph Laplacian has been studied, especially by Fan Chung, and some with Fan Chung and Yao. And so what we're doing is extending that in these different directions. First of all, to higher order Laplacians, Hodge operators, and also to the continuous limit, and try to understand the relations between the finite Hodge theories and their continuous limits. Okay, and I should say here, this group here is not the same as the group I'm talking about here. It's closely related because here we have an L2 cohomology. So, for example, in the Schick example, we don't know if the ordinary cohomology is finite or not. But we know that this has to be no, let's see, this implies this. So if we knew this, we would have this, but this is the L2 version, which is harder to analyze. And this uses the spectral sequence argument. Okay, so this is beginning to give a pretty good introduction to what we've been doing. And we still, as I say, have so many more questions than answers. For example, take this problem here. Suppose we have a solution of this. Is F continuous? Just take it in general. Compact metric space is a measure. And suppose we have, it solves this equation. Is F continuous? We don't know. We don't know of any counterexamples. And we don't know any results except maybe very low dimensions. And in very, very obvious cases, we don't know. We discussed this. These problems allowed. These things are discussed in our paper, which is on the website. But let me just stop here. Thanks very much.
I think we have a little time if there's any quick questions for Smale.
Yeah.
The spirit of Poincaré.
Yeah.
And I ask, is there a fundamental proof as well as homology?
Oh, that's a good question. And the trouble is there's maybe more than one way to go on that. Yeah, one wants to think about some kind of a finite version of Poincaré's conjecture. But one has to be careful before one says what it should be. Because the fundamental group especially brings in some problems. And what does one want for a homeomorphism? So there's something to think about. But there's so many questions. Just this understanding this finiteness question has already got so many obstacles to it.
Any other question? In the case when you start with a smooth manifold and generate a random set, does the non-zero spectrum of this Laplacian approach the spectrum of the ordinary Laplacian? Is that
Well, that's something. The alpha goes to 0.
Yes. That's,
one has to be careful about that. First of all, our operator is a bounded operator. And the classical Laplacian is unbounded, so the spectrum goes to infinity. So one has to say how that spectrum corresponds. So there's going to be some kind of change, transformation. And then it might be true, but we spent a lot of effort on that. And we know people in other aspects of this subject have been caught with this problem. It's not those kind of problems are not easy at all. In very much more classical settings, when you go from some kind of integral operator like this to the classical Laplacian even, one has problems. We have some results for L equals 0. So we have a pretty good picture for L equals 0 for just just for potential theory. So all this for L equals 0 is just an extension of potential theory. Then a lot of these problems are solved, and one has some kind of a extension of potential theory to compact metric spaces.
All right, if there are no other questions, let's thank Professor Smale again.